G'day, g'day. Welcome to our third and final lesson into our fourth unit on states of matter. In this lesson, we are looking at the solid state and lattice structures, where our lesson objective is to investigate the lattice structures responsible for the solid state. As always, our learning outcomes we are addressing in this lesson. In the previous videos in this unit, we've looked in depth at the gaseous state, we've looked in depth at the liquid state, and we've looked in depth at the phase changes between those. Let us finish all this by looking at the solid state and how our particles arrange themselves within the solid state. So we've got to bear in mind all the stuff about kinetic theory and particle theory, the idea that all matter is made up of small particles that is in constant movement. In the solid state, we have our particles with a fixed volume and fixed shape arranging themselves in a very fixed, a very structured three-dimensional lattice like so. We describe this as a crystalline arrangement, crystallining meaning the arrangement of particles into a highly ordered microscopic structure called a crystal lattice. Four types of lattices we're going to look at in depth: our ionic lattices, metallic lattices, and then we have two types of molecular lattices. The strength and nature of bonding between the particles will determine its physical properties. So to begin with the ionic lattice, also called giant ionic lattices. If we think back to our ionic structures are made up of cations that are positively charged, that have lost electrons, anions negatively charged, that have gained electrons, a strong electrostatic attraction between those two kinds of ions. And what they do is the positive and the negative attract themselves and they'll fix themselves into a very fixed, a very ordered three-dimensional lattice like is shown up here, where we have an arrangement of positive, negative ions like so. So ionic lattices have three-dimensional arrangements with alternating positive and negative ions. The type of lattice will depend on the size of the ions. So we know from our periodic table, depending on how many protons, how many neutrons, how many electrons, we have different sizes of the atoms. So consequently, we're going to have different sizes of the ions when they gain or lose those electrons. So which kind of lattice they will make up will depend on how big these ions are. For example, sodium chloride is just going to be a simple cubic lattice. If we think in three dimensions, so we have our y-axis, our x-axis, but then in three dimensions, so this would be a two-dimensional shape, a square. I'm sure you're familiar with a square. But when we go into the third dimensions, we have to include the z-axis. So we have to consider our lattices in three dimensions. It's very hard to do with a ruler, so I'm just going to freehand as best I can. So we have a three-dimensional arrangement like so, where our sodium chloride, a simple lattice, is just going to have alternating sodium to chloride ions electrostatically attracted to each other. So chlorine is a bigger atom than sodium. So we're going to have large chlorine ions, and then that's going to alternate with smaller sodium ions. Sodium ions, the positive and the negative, are going to attract each other. We're going to have a large chlorine ion like that. Then we're going to have sodium alternating positions. Chlorine minus there, chlorine minus there, and a smaller sodium ion. So very fixed, very ordered, very structured. There are different kinds of these types of lattices depending on how big they are. For example, and the good news is with our curriculum we don't need to know each of these in depth, but it's worth touching on. We got things like simple cubic, where this would be our simple cubic. We have a sort of a cube arrangement and it's simply the four corners of the cube. We have things like body-centered and face-centered cubic structures, where we have a few extra particles within the cube. So if I draw another three-dimensional cube, like so, if we have body-centered, we would have a ions sort of at each corner like we have there, but then we would also, I'll just do it all the same color, but then we would also have particles, one single one in the center of the cube. So it's body centered. There's a If you imagine this is sort of equidistant from each of these in the center of the cube like so. And then you can also have face-centered cubic structures where you have a particle in each face of the cube. Now this is going to be a little bit trickier to show, and hopefully it doesn't get too ugly in the pictures. But if I have that face there, I have a particle in the center of the face. This face at the back there, I have a particle in the center. This one on the side, a particle in the center. This one in front, the one on top, and the one beneath. And then on top of that, we have our particles all on the corners like so. So different ways, depending on the sizes of the particles, that they can arrange themselves. Like I said, the good news is we don't know these by name, but it's worth just being aware that they exist. Let's consider some of the properties that will manifest as a result of this kind of lattice. Ionic lattices have high melting points because we know we have a very strong electrostatic force of attraction between positive cations and negative anions, and we know it's going to take a large amount of energy to disrupt that. So it's going to take a large amount of energy to disrupt our three-dimensional lattice and make it go into the liquid form. This will increase with charge density. So if we've got a +1 ion and a +- ion, this is going to have a lower melting point than if we had a +2 ion and a -2 ion. The stronger the charge is, the higher the melting point will be, because there's a lot more charge, there's a lot more attraction between those charges because they're greater. So it's going to take more energy to overcome that. They're brittle. That means that if you were to bend it, unlike this metal ruler which is bendy, if you were to apply pressure to an ionic substance, it would snap. It would be a brittle thing. Applying pressure can force like charges to get closer. We know that like charges repel each other. This repulsion among numerous ions in the structure will cleave the structure along this plane where we have all of these like charges repelling each other, and as a result, that will cause it to snap. They're hard. That also comes down to the strong force of attraction between the positive and negative cations and anions. Difficult to scratch the surface due to strong attractive forces. They're soluble in water. We discussed that in a previous video, but essentially we know that water is a polar molecule. Water has a positive end, it has a negative end, and that can essentially, our water molecules can get in to our ionic substances and disrupt the negative and positive charge between it. So if we've got water that has a delta positive end and a delta negative end, a bunch of water molecules with their delta positive ends can surround the chlorine atom and essentially sort of break the electrostatic attraction between all of these ions. And finally, they will only conduct when they are in the molten phase, so when they're a liquid or when they're in solution. Charge is a flow, conductivity is essentially the ability to conduct a charge. So you need a charged species that can move. In the solid state, they're very fixed in place. They can't move, they're still vibrating. However, they're not able to move, so you can't conduct a charge. It's only once you disrupt that three-dimensional lattice where the ions can move, such as in the liquid or when they're in solution, then you can conduct a charge. Right, so that's our ionic lattices. So when we're thinking about why these lattices form, just remember that all matter just wants to exist in the lowest energy that it can. So these lattices that they form based on the charge or based on the size, all comes down to that attraction between the ions and them just finding a way to exist in the lowest energy state that's possible for them. And that's when we get these different kinds of lattices. So onto our metallic lattices. If we think back to our metallic bonding model, our metallic lattices consist of positively charged metal ions surrounded by a sea of delocalized electrons. So if we have a metal such as magnesium, magnesium group 2, magnesium forms a 2+ ion. So a metallic bonding is a whole bunch of magnesium ions in a fixed three-dimensional lattice, very similar to our ionic lattices. And then the electrons they lost become delocalized between them. They're free to move around. And this strong electrostatic force of attraction between the positive cations and the negative electrons is the metallic bond. So this sea of delocalized electron is called a sea because it's able to move and flow, not unlike an ocean. So we have our metallic lattice where they arrange themselves in fixed three-dimensional lattices very similarly to what the ionic lattices did, often in hexagonal layers or a cubic arrangement. Rightio, so we can rationalize a bunch of physical properties that we observe in metals, such as their high melting points. Strong force of attraction between the electrons and the cations means a lot of energy is needed to go from the solid to the liquid phase or from the liquid to the gaseous phase, thus high melting points. Due to the strong metallic bonds, they're malleable and ductile. So unlike the ionic substances that were very rigid and very fixed in shape, in their shape, these sea of delocalized electrons that are constantly moving allow the cations to slide over one another. So the layers can slide, metallic bonds can reform due to the sea of delocalized electrons. So on my diagram here, if I were to apply pressure here, this layer can essentially slide over the other layer. So I've got my other layer down here. This layer can slide over and the metallic bonds can still be maintained because the sea of delocalized electrons is able to move. Hopefully that sort of shows it a little bit. But they're able to slide over each other so we can get malleable metals. So unlike our ionic substances that would snap, our metals can bend and they can be stretched. They're ductile. Malleable means bendable, ductile means stretchable. And they're good conductors because they have this sea of delocalized electron that can very easily conduct a charge. Rightio, so we have these things called alloys that's worth touching on as well. Alloys is a mixture of two or more metals or a metal and a non-metal. So you often think of mixtures as maybe a mixture in the liquid or a mixture of solutions. An alloy is a solid mixture. So we have a additional metal cations or even non-metal particles such as carbon that mix and make an alloy, and we can change the properties of metals because of this. It disrupts the uniformity of the lattice so the layers can no longer slide with ease, and that's due to the different sizes of the particles, the metals that would be present. So unlike here, because it's a very uniform arrangement and they can slide over one another, if we had a different metal in there that was a lot larger, it would disrupt the ability for the layers to slide, and consequently it would become a harder, less malleable substance. It will make it stronger. For example, brass is a mixture of copper and zinc, and brass is something that was used to make lots of things like armor and weaponry back in the day. Now on to our two types of molecular lattices. We're going to first look at simple molecular lattices. So simple molecules can also form crystal lattices. For example, iodine is a solid at room temperature. Carbon dioxide, dry ice, has a face-centered lattice that we can see over here. So the same thing that we saw before, it's only with molecules instead of ions or instead of metals. In this case, we've got carbon dioxide molecules forming a face-centered lattice. So we have a very even distribution of the carbon dioxide molecules at each corner and then within each face of the cube. So let's just recap. Whilst covalent bonds, whilst our intramolecular forces are very strong, the forces between molecules, our intermolecular forces, are much weaker. We have a whole video on intermolecular forces that you can go back and recap on if you want to do that. So let's consider the physical properties that will manifest because of these chemical properties. They will have low melting points because we have weak forces between the molecules. So it doesn't take a lot of energy needed to overcome the intermolecular forces between the molecules. So this is very different to our ionic and our metallic ones that have high melting point because it takes a lot of energy to overcome those strong forces of attraction. It just takes a small amount of energy here. They don't tend to conduct because they don't really have charged particles. And in general, they tend to not be very soluble, but it does depend on the polarity of the molecule. Like dissolves like, that's something that we talked about very briefly in a previous video. And then we had our hydrogen bonding, which was our strongest force of intermolecular forces. It was an extreme case of dipole-dipole that was a bit stronger than dipole-dipole, but not as strong as a covalent bond. So it's worth noting here because there can be some slightly different things. especially for water. Hydrogen bonding in water is much stronger, so it can increase the melting and boiling points. It inhibits the ability for molecules to slide over one another. That increases the viscosity, which is a word for essentially the thickness. And then we have a higher surface tension that results due to the downward force from hydrogen bonding on the surface. Now onto our giant molecular lattices, which is something that we haven't looked at all. A giant molecular lattice is a three-dimensional lattice of covalent bonds throughout the structure, also called macromolecular structures. Macro meaning large scale, the opposite of micro. So there are no intermolecular forces present, only covalent bonds between all of the atoms. So unlike our small molecules that have intermolecular forces, our giant molecular lattices have no intermolecular forces because it's essentially just one giant molecule. It's just a whole bunch of atoms, and every single atom is covalently bonded to one another. We said just before that covalent bonds are very strong. So this is going to have some inference for the physical properties of our macromolecules. They have very high melting points. Because covalent bonds are very strong, it takes a large amount of energy to overcome that. The hardness and conductivity will vary, and that depends on the specific structure, and we're going to look at a few specific structures in just a moment. But we do need to introduce a new piece of vocabulary, which is this word allotropes. We can have different macromolecular structures of the same atom. So the word allotrope describes the different crystalline or molecular forms of the same element. For example, diamond and graphite are both just carbon atoms. They're just bonded in different ways. So we would say that diamond and graphite are allotropes of one another. Let's look at some of these macromolecular structures. All right, what have we got here? Diamond. The first one we're going to look at is diamond, which looks like this. This is essentially just a carbon atom, sp3 hybridized in a tetrahedral arrangement, bonded to 4 other carbons that are also tetrahedral sp3 hybridized. So I have a carbon, I have my tetrahedral arrangement like that, and each of these covalent bonds is bonded to another carbon that is also sp3 hybridized, bonded to 4 other carbons in a tetrahedral arrangement, and then we get these bonded to each other, and it all becomes interlocking and very strong and very ordered, and it would look like this diagram here. Because of this, it is very hard because of the strong covalent bonds, and it is not conductive because there are no charged particles that are free to move. Silicon dioxide is another, or silicon oxide, is another type of macromolecule that's similar to this diamond structure. Silicon is tetrahedral and sp3 hybridized, so it will have this similar arrangement of atoms. Each silicon is bonded to 4 oxygen atoms. Each oxygen bond is bonded to 2 silicon atoms, so it will have silicon dioxide SiO2 as the chemical formula. Similarly, it is hard and non-conductive. Now we also get graphite and graphene. So these are allotropes of carbon. So it's an allotrope of diamond. The graphite and graphene are these arrangements here. So graphene is just one layer of an sp2 bonded carbon in a hexagonal lattice, whereas graphite is composed of many graphene layers. So graphene is just one layer, graphite is lots and lots of these layers on top of each other. These layers are, this graphite is soft as the layers can slide over one another, so it's got a soft physical property, and it has one delocalized electron from each carbon between the layers, so it can conduct electricity. As you can see here, each carbon just has 3 bonds, so that means there's 1 electron that is delocalized in between these layers for each carbon atom. Graphite is your lead pencil, so essentially when you're drawing with a lead pencil, what you are doing is just sliding layers of graphene away from one another, and that makes the marks on your paper. So allotropes of carbon, diamond, graphite, and graphene, and then our other macromolecule, silicon oxide. To finish today, we just need to discuss briefly the idea that there's a finite nature of material on planet Earth. We get metals from ores, and this consumes a lot of energy, and a lot of the ways that we consume these metals can be very bad environmentally, have a very negative impact on the environment. There is only a limited supply of metal ores in the Earth, and they cannot be replaced once they are used up. Our energy resources, the energy we use to extract the metal is also finite. And a vast amount of the things that we make end up thrown away in dumps and landfills that again have lots of negative environmental implications. They're a bit of an eyesore, they smell bad, they're not the nicest things in the world. We can reduce a lot of these things through recycling. Recycling has a number of advantages. It saves energy, it conserves natural ore resources, it's cheaper than extracting metal from the ore, and it reduces wastes and the need for dumps. But it's not always easy to recycle. You need to properly collect and properly sort the different materials in order to recycle them effectively and efficiently. And you also need the transportation. You need the ability to pick up and transport the recycled material to recycling plants. It also depends on issues regarding supply and demand, if there is enough recycling available in order to meet the supply and demands of our everyday lives and the things we want to build and the way we want to live. So there's a lot of sort of balancing act between how we can protect the planet and the environment and also still, take advantage of the lifestyles that we have and the things we like to do. But I mean, the reality is that we only have one Earth, and we've really got to take care of it. A lot of the things we're doing at the moment are just absolutely destroying it. So things like recycling, even just from our own little corner of the Earth that we do it in, are really, really important things and can have really positive, far-reaching implications if we do it and if we promote a sustainable lifestyle. Excellent, and with that we finish our lesson and our fourth unit. What have we done? We've described in simple terms the lattice structure of ionic, simple molecular, giant molecular, hydrogen bonded and metallic structures. We've discussed the finite nature of materials as a resource and the importance of the recycling process, outlined the importance of hydrogen bonding to the physical properties of substances, and suggested for quantiphysical data the type of structure and bonding present in a substance. Your tasks, if you would like to do some work to consolidate it, pause the video, one column at a time, working from the bottom up to the top. Thanks for joining me on this States of Matter unit. I will see you on the next one when we start Unit 5. Have a fab day.